Hello everyone, welcome you all to this video lecture. So in this class, we'll be trying to discuss all those MCQs which were there in Basic Mechanical Engineering Quiz 1, right? So without wasting time, let us move forward and start our discussion. So this is the first question which is with me right now. Okay, so let us read it. It is saying that an ideal gas undergoes a constant entropy which is isentropic process in a closed system. The heat transfer and work are respectively what? So we need to find out the heat interaction and work interaction for this particular process which is happening isentropically for this particular ideal gas, right? Okay, so isentropic, we know the other name of this particular process is as the reversible adiabatic process, right? So reversible adiabatic process can be called as the isentropic process, right? So we can now think of an adiabatic process which is done reversibly, which is known as the isentropic process, right? And if we'll be talking about any reversible adiabatic process, of course there is no heat interaction, right? Okay, so let us try to understand by using the first law of thermodynamics when it is being applied to any process, right? So for any process, I can write this particular equation, that is del q will be equal to dE plus del W. Okay, and if I'll be neglecting the changes in kinetic energy and potential energy, then I can rewrite this particular equation by this form, that is del q will be equal to du plus del w, right? Now if I'll be writing this particular equation energy in the form of energy per unit mass, right, then I can rewrite this particular equation by del q will be equal to du plus del w, right? So all these forms of energy which are there, these are in the form of joule per kg, okay, or energy per kg. Okay, now as I have told you, for a reversible adiabatic process, reversible adiabatic, right? So simply adiabatic simply means there is no heat interaction, and that is q equal to 0, right? So no heat interaction. So in this process, del q will be equal to 0, right? So heat interaction will be equal to 0, right? So if I'll be putting this del q value is equal to 0, then I can rewrite this particular equation by this, right? This will be equal to du plus w or del w. Okay, now for ideal gas, for any state change, I can write this du by cv dt, right? So I can write 0 will be equal to cv dt plus del w. Now from here I can find out del w will be equal to minus cv dt, right? So here del q is equal to 0 and del w will be equal to minus cv dt. So here option A will be the correct answer. Okay, done. Moving further towards the next question. Okay, now in this question, it is saying that heat flow into a system is gas and the heat flow out of the system is gas. So it is talking about the sign convention of heat interaction, right? So we know if I'm taking any system and if I'm adding some amount of heat to the system, that is considered as positive, right? And if some amount of heat is getting rejected from the system, that is considered as negative, right? That means heat added to the system is positive and heat rejected from the system is negative. Similarly, if we'll be talking about the work interaction, then work added to the system, that will be taken as negative, and work we obtain from the system W, that will be taken as positive, right? So work done on the system, that is negative, and work done by the system, that will be positive. Heat added to the system, that will be positive, and heat rejected from the system, that will be negative. So here heat flow into the system, that will be positive, and heat flow out of the system, that will be negative. Okay, so option D will be the correct answer. Hope it is clear. Okay, so let us move further. Okay, so now this is the question: which of which among the following statements regarding the differentials of path function is true, right? So it is talking about the differentials of path function. That means it is talking about the path function, right? And we know there are two path functions basically, and in thermodynamics basically we are having three path functions, right? One is your heat interaction, another is your work interaction, another is your entropy generation, right? Okay, so let us talk about the heat interaction and work interaction basically. So if I'll be writing del q, actually I cannot write this is as q2 minus q1. Okay, so this is a path function which cannot be written like this. Similarly, del w cannot be written as w2 minus w1, right? So these are not the exact differentials, right? But I can write de will be equal to e2 minus e1, because this is an exact differential. Done. Okay, let us read the statements. The differential of path functions are exact differentials, so this is not the correct one, right? Next, the differentials of path functions are not exact differential, so this will be the correct answer. Okay, so let us read third statement as well. Path functions have same value for different processes for any state change. No, this is not the correct one. That means path functions are dependent on the path. Okay, so that is why it will be having different values. Okay, for any state change it will be processing, it will be doing some different processes. For different processor will be getting some different path functions, right? The values of path functions will be different for different path for any state change. Okay, so this will be also the wrong one. So correct statement will be the second one, option number B. Hope it is clear. Moving further towards the next question. Okay, so next question, let us read it. Which device is used for the expansion of refrigerant in vapor compression refrigeration cycle, right? So already we have idea about the vapor compression refrigeration cycle, and we know different components which are there. Okay, so there are basically four components, right? Hope you remember. Still let me recall about it. So there are basically four components. What are they? There is evaporator, right? Okay, then there is a compressor. Okay, so first one is here evaporator, then compressor, then there is a condenser, and there is an expansion valve, right? Okay, we can draw this is somewhat like this. So this is an expansion valve, right? Okay, so our cycle will be moving somewhat like this. So from here to here, then here to here, then here to here, then from here to here, then like this, then like this, then like this, and like this. Okay, so it is an actually anti-clockwise cycle, right? So if we'll be talking about an engine, that is a clockwise cycle, but if we'll be talking about the refrigeration cycle, then this is an anti-clockwise cycle, right? So our refrigerant will be moving like this. Okay, so now I am interested about the expansion process, right? So expansion process will be happening in the expansion valve, and sometime we can call this is as a throttling valve, and we can replace throttling valve by the capillary tube as well, right? So this expansion process, the expansion of refrigerant, it is happening inside the throttling valve or capillary tube, right? So option C will be the correct answer for this particular question, right? So what is happening in case of your evaporator? So evaporator is taking heat from the surrounding to the refrigerant, right? What it is doing? So it is taking heat from the surrounding or the refrigerated space to the refrigerant. Okay, so heat is taken from the surrounding to the refrigerant. Done. Okay, so in compressor, what is happening? The refrigerant which is moving into the compressor, the temperature and pressure of the refrigerant increased by addition of some amount of work to the compressor. That means compressor, some work will be given to the compressor. Due to this work interaction, the temperature and pressure of the refrigerant is going to increase, right? Then so high temperature refrigerant will be moving into the condenser, and this there is a heat rejection from the refrigerant to the surrounding, right? So in this case, the refrigerant will be rejecting heat to the surrounding. Done. Then after that, the refrigerant will be sent to an expansion valve. In that case, in that particular device, the expansion of refrigerant will be occurring. Done. Okay. So in this question, option C will be the correct answer. Okay. Next. So in this particular question, the law. So it is talking about the law which provides the basis of temperature measurement. Okay. So easiest one, we know the zeroth law of thermodynamics, which is talking about the thermal equilibrium. That means suppose there are three bodies. Okay. So there are three bodies or three systems we can say, and this system A, and this is B, and this is C. Suppose A is thermally equilibrium with B and separately thermally equilibrium with C, then these two bodies these two systems are also thermally equilibrium with each other. So by using this particular law, we are measuring the temperature, right? So temperature measurement devices are basically using this particular methodology or principle, right? Okay, so option B or this particular zeroth law of thermodynamics, second option will be the correct answer. Okay, moving further now here. Okay, so in this question, this is a question from the IC engine. Okay, let us read it. In 4-stroke petrol engine, each stroke consists of dash degree or dash of crankshaft rotation. Okay, so let us revise something with this. Okay, already we know. So it is talking about the petrol engine. It actually doesn't matter, and here it is talking about the 4-stroke petrol engine. Okay. So if I'll be showing the arrangement, let this is the cylinder, and let this be any piston which is there, and it is now placed at the top dead center, and now it may move from top dead center to the bottom dead center as well. So this is the bottom dead center. Okay, so this piston will be connected with connecting rod. Okay, now this will be the vertical position of the connecting rod at this particular instant, and your connecting rod is connected to the piston at the gudgeon pin, right? Do remember it. So the connecting rod, which is this one, is connected to this piston at this particular pin, which is known as your gudgeon pin, right? And this connecting rod is connected to crank. So this is the crank again, which is at the vertical position. So this is connected, there is connecting rod is connected to crank at the crank pin. So this is the crank pin and this is the gudgeon pin. Okay, and this is crank, this is connecting rod, this is piston, and this is your cylinder. Okay, now here it is asking about a stroke. Stroke simply means when our piston is moving from one dead center to another dead center. It may be from TDC to BDC, or it may be from BDC to TDC. It doesn't matter, right? So now let us consider the movement of piston from TDC to BDC. Okay, so during this particular movement of piston, what will happen? This crank, which can rotate about this crankshaft. So this is what? So this is crankshaft, right? So this crankshaft can rotate about this particular crankshaft. This crank can rotate about this crankshaft. Done. Okay, so when this particular piston is moving down, in that case our crank will be start rotating. Okay, so it is moving down and it is moving clockwise, right? So when it will be moving down, so it will be moving it will be doing some rotational motion like this. Okay, and when this particular piston will be reached at this particular bottom dead center, okay, so at that particular time our crank will be at this particular point. That means the crank pin will be at this particular point. Okay, so during one stroke, that means during one movement of the piston from one dead center to another dead center, our crank has done this particular movement. That means rotation, it has done up to this particular limit, right? So the crank has moved from this point to this point, right? So now in this case our question is to find this particular angle. So how much angle our crankshaft has been rotated, right? So what is this angle? This is nothing but your 180 degree. Done. Okay, so here option C will be the correct answer. Done. Moving further. Okay, so here it is asking about the reversibility, right? Let us state it. The condition for the reversibility of a cycle. Okay, so what is the condition for which I can or we can call a cycle to be reversible? Okay, so what could be the condition? So first and last condition we can say all the processes must be reversible, right? Most important one, in a cycle there will be number of processes, right? There may be number of processes. Okay, so all the processes which are present in any cycle, those processes must be reversible. Okay, that means for reversible, what are the conditions? Like we have known, the a process is said to be reversible if the initial condition can be regained by the same path without affecting the conditions of system and surrounding. Such a process is known as the reversible process, right? So what I told that the initial condition of the system can be regained by the same path without affecting the condition of the system and surrounding, that is known as the reversible process. Okay, so to do so we have to maintain the pressure, temperature and all these equilibrium conditions, right? And if we'll be trying to maintain all these equilibrium conditions, that means all these processes which will be doing, all the processes must be very slow. That means it will be quasi-static, right? Quasi-static processes are very slow process. Okay, and in that case we'll be neglecting all these frictions, right? Okay, so let us see what are these options. So here it is saying that the pressure and temperature of the working substance must not differ, right? Differ appreciably, right? So there will be no large change in all these properties, right? From those of the surroundings at any stage in the process. At any stage of the process, there will be no change, appreciable change in pressure, temperature of the working substance. Okay, so this can be the answer. Obviously, I have told you, right? Okay, next statement it is saying that all the processes taking place in the cycle of the operation must be extremely slow, kind of quasi-static. So this can be also the answer. Then the working parts of the engine must be friction free. Again, we will be neglecting all these frictions. Then this can be also the answer. That means all these three options can be correct. Okay, or so actually they are correct, right? So here fourth option it is saying that all the above option. So option 4 will be the correct answer for this particular question. So this is the appropriate option to be ticked, right? So here option D will be the correct. Okay, let us move further now. So here in this question it is again talking about the IC engines, where it is especially talking about the CI engine. Okay, CI, it stands for your compression ignition engine, right? So let me write it down over here. This is compression ignition engine. Okay, not combustion ignition. So this is compression ignition engine, right? Okay, so in CI engine, fuel supply is controlled by which device, right? So in case of a CI engine, which device is used to control this fuel supply? Let us read the statements or read the devices. Option A, it is saying that throttle valve, right? So normally we don't see throttle valve in case of your CI engines. Actually we see this in case of your refrigeration system, right? So this is not used there. And spark plug, again this is used in case of your SI engine. SI simply means spark ignition engine. So spark plug it is not present in case of your CI engine. So this is also not the correct option. And fuel pump, so this is the correct one, correct option, that fuel pump controls the fuel supply, right? So option C will be the correct answer for this particular question. Moving further. Okay, so question number this one. Okay, so you need to find out the ratio of absolute temperature, that is T2 by T1 at two different states in an adiabatic process, right? So temperature and options are given in terms of pressure. So we have to find a relationship between temperature and pressure, right? Temperature and pressure. Okay, for the process adiabatic. Okay, so for adiabatic process we can write this is PV to the power gamma equal to constant, right? And of course if we are talking about the process, then there will be two states which will be joined by a path. Then for this particular states I can write P1 V1 to the power gamma, that will be equal to P2 V2 to the power gamma, right? And I can write P1 by P2, that will be equal to V2 by V1 raised to the power gamma. Okay, so this is the relation which we got over here. So this is the relationship between pressure and volume, but here we are asked to find the relationship between pressure and temperature. Done. Okay, so let us try to convert this volume in terms of temperature, right? So how can we do that? We have our ideal gas equation with us, right? We know this is PV equal to mRT. Okay, and from here if we are trying to find out volume, then I can write this will be equal to mRT by P, right? So for state 1, if I'll be trying to find out the value V1, that will be equal to mRT1 by P1. Similarly, I can write V2, that will be equal to mRT2 by P2. Okay, so let us try to put all these values, that is V1 and V2, in this particular equation. Then I can write what? That is P1 by P2, that will be equal to V2, that simply means mRT2 by P2 divided by mRT1 by P1, right, and raised to the power gamma. Okay, and from here I can cancel this mr and this mr. Now I can rewrite this particular equation by this T2 by T1 to the power gamma into P1 by P2 raised to the power gamma. Okay, now let us solve it further. Okay, now I can write, so I can take this particular pressure term to left hand side. I can write P1 by P2 into okay, so let us divide that. Okay, so if I'll be multiplying by taking this to that side, then I can write, okay, did we make any mistake? No, right? So if I'll be taking this P1 by P2 to that side, then I can write what? Okay, so this will be divided by P1 by P2 raised to the power gamma, and that will be equal to T2 divided by T1 raised to the power gamma. Okay, now if I'll be taking this numerator to the denominator, then denominator to numerator, then I can write P1 by P2 raised to the power 1 minus gamma, right, and that will be equal to T2 by T1. Okay, now if I'll be writing this particular term, this is okay, there is gamma. Now if I'll be trying to find out the value of T2 by T1, then T2 by T1 can be represented written by like this P1 by P2, which is 1 minus gamma divided by gamma, right? Okay, so let us check the options which is given to us, that is T2 by T1 equal to P1 by P2 1. So this is not the correct one, right? So this is not the correct one, and P1 by P2. Okay, so all these forms are given in terms of P2 by P1. So let us try to convert this into P2 by P1. So I can write T2 by T1, that will be equal to P2 by P1, and here we will be taking negative sign, so that will be gamma minus 1 by gamma, right? So here now we are matching with this particular option. This one, option B, will be the correct answer for this particular question. Okay, so moving further, hope it was understandable, right? So try to derive, and definitely this is not a difficult one, easy one of course, right? Okay, now so this is another question. For CI engine, the compression ratio varies between what? So range, we can say this is 14 to 22, right? So 14 to 22 for CI engine, and 16 to 12 this is for SI engine, right? So compression ratio, it is high in case of your CI engine and less in case of your SI engine. So here option B will be the correct answer, right? Next question. Okay, now here it is talking about the evaporation process of vapor compression refrigeration system, right? So in evaporation process of vapor compression refrigeration system, what is happening, right? So already I have discussed about that if we'll be talking about the evaporation process, here the refrigerant will be going into this particular device, and here it will be moving out, and during this what it is doing, it is taking heat from the surrounding to the refrigerant, right? So let us read the statements. Heat is rejected heat is rejected from refrigerant to surrounding. No, this is not the correct one. That means here refrigerant is accepting heat, right? Is getting heated. So here next statement, heat is rejected from surrounding to the refrigerant. Okay, so this is the correct one. That means the surrounding is rejecting heat to the refrigerant, right? So refrigerant is getting heated. So option B will be the correct answer for this one, right? Still, let us read the other statements, right? Only pressure changes take place. No, there is no change in pressure actually. Okay, so here option B will be the correct answer. Moving further. Okay, so here, so which of the following equalities or inequalities it is true for all reversible heat engines operating between two constant temperature thermal reservoirs at temperature TH and TL, and in this case TH it is greater than TL, right? So TH is greater than TL. Okay, so in this figure, okay, so this is TH and this is the reservoir. We can call this is at the source, okay, and this is the reservoir. We can call this is as the sink, right? So this is source and this is sink, okay, and this is any heat engine, right? Okay, for this particular cyclic device, obviously heat engine, it is a cyclic device, and during this cycle, what is the relation? Okay, so we know, and this is talking about the reversible heat engine, and for the reversible heat engine, from the second law of thermodynamics, we know the cyclic integral of del Q by T, it should be equal to 0, right? That simply means these two statements or these three statements are wrong, right? So maybe this is correct or maybe this is correct. Okay, now we are active about this heat interaction, right? So heat interaction, if we will be trying to find out the amount of heat is added, that is QH over here, and the amount of heat is getting rejected, that is QL over here, and we are getting some amount of work W. In this case, if we will be trying to find out the net heat interaction, that will be equal to what? That will be QH minus QL, right? So this will be del Q, and QH is greater than to QL. That means this negative will be having positive value. So this difference will be having positive value. That means we can write summation of del Q will be greater than 0, right? So this integration, simply we are saying we are calculating the heat interaction during the cycle, and during the cycle there is two heat interaction. One is added to the system and one is getting rejected from the system, right? And the net heat interaction, that will be equal to del Q, which is positive. That simply means this net heat interaction will be greater than 0. So option E will be the correct answer for this particular question. Okay, hope it is clear. Moving further. Sorry. So let us read the question. Consider the following statements. Okay, so 1, a reversible adiabatic process must incur no change in entropy of the system. Okay, it is true, because if we are talking about the reversible adiabatic process, in that case there is no change of entropy, and we can call this is the isentropic process, right? So statement 1 is correct. Okay, statement 2. A process with no change in entropy of the system must be reversible and adiabatic. So this may be possible or this may not be possible actually. So this statement is wrong. Okay, because if I am saying any process is reversible adiabatic, then that can be called as the isentropic process. But all the isentropic processes are not reversible adiabatic. Okay, so we can write down this del S. Okay, entropy change will be equal to del Q by T plus S generation. Okay, if we'll be talking about any reversible process, in that case this, so this term will be equal to 0. Okay, and ds will be equal to del Q by T in case of your reversible process, and this we got from the Clausius inequality, right? So del Q by T will be less than or equal to 0, right? So del Q by T will be equal to 0 for reversible process, and that will be equal to del S only. right? So we can write del q equal to t ds in case of the reversible process, right? So if there is no heat interaction, right, so there is no heat interaction, there is no change in entropy, right? So reversible adiabatic, that simply means our entropy change is negligible, zero. But if we'll be talking about isentropic, that means this is zero. This doesn't mean it will always be reversible and adiabatic. It may happen, it will be having suppose some negative value, then it may be having some positive value, right? So it may be irreversible and some other processes, right? So this is not always true, but this is correct one. So option statement 1 is correct and statement 2 is not correct, right? So option A will be the correct answer for this particular question. Okay, so moving further. Okay, so in this question it is saying that in the polytropic process equation PV raised to the power n equal to constant, where if n is infinitely large, the process is termed as which process, right? So we are given with a polytropic process which is following this PV to the power n equal to constant and if sorry, if n is equal to infinite, so n, if it is infinite, then we know this is the process of volume constant, right? So volume constant, that means isochoric process, so constant volume process. So option A, option first statement, option first option is the correct one. Done. Okay, moving further. Here work done for an isothermal process is what, right? Work done for an isothermal process, right? If we'll be trying to find out that, we know W equal to integration of P dV from statement 1 to statement 2, and for isothermal process we can write PV equal to constant, and from here I can find out the value of P, that will be equal to C by V, and if I'll be replacing this particular term over here, then I can write W will be equal to integration of P, where this will be equal to C by V into dV. Okay, from 1 to 2, then C can be taken out, so here C and dV by V integration will be equal to ln V2 by V1, right? Where C can be replaced by any value, right? So W can be written as P1 V1 ln. Okay, so here V2 by V1, so in any term we are not we cannot see that V2 by V1 term, so otherwise I can write P1 V1 equal to P2 V2. So from here V2 by V1 can be written as P1 by P2. So this W can be written as P1 V1 ln P1 by P2. So here option C will be the correct answer. Hope it is understandable. Moving further towards the next question. Okay, now here consider a heat engine that operates on a cycle, receives given amount of heat, that is QH, okay, from a high temperature reservoir and does an equal amount of work W, that is equal to QH, as shown in the figure which is given below. So which among of the following statements about this heat engine is true? So we need to find out which statement is true, right? So if it will be looking into this particular configuration which is given to us, so this is the high temperature reservoir, we are extracting this amount of heat, that is Q, and we are supplying to a heat engine which is supplying some amount of work, and that is equal to QH, right? So in this case actually if we'll be looking into, it is violating the second law of thermodynamics, right? Of course it is not violating the first law, because energy interaction, no, that is in terms of heat will be equal to energy interaction in terms of work, right? Net energy interaction, right? So QH, or the energy which is going into the system, that amount of energy will be going out of the system, that is QH will be equal to W. So this is correct according to the first law of thermodynamics. So it obeys the first law, but it is not obeying the second law, because what is second law? According to Kelvin Planck statement, it will be impossible for us to make a device which will be converting the heat into work interacting only with a single reservoir, right? So we can see only a single reservoir over here. There is no other reservoir to which the system or the heat engine is rejecting some amount of heat. So that is why it is violating the second law of thermodynamics, right? So that is why we can take. So it obeys the both first law. No, this is the wrong one. It violates the first law. No, it obeys the first law. Okay, so it obeys the first law. Okay, and violates the second law. So this is the correct one, right? Okay, so option C will be the correct one for this question. Moving further, so this is the match of the following type question. Boyle's law, obviously we know this is PV equal to constant, okay, where temperature equal to constant, right? At constant temperature, pressure volume relation is inverse. Okay, Charles law, at constant pressure, okay, at constant pressure, volume and temperature has the direct relation. So this one. And Gay-Lussac law, at constant volume, pressure and temperature has direct relation, right? So A2, so these two are the wrong options, or wrong option, okay. And B, so B is matching with option number 3, so this one. So option number 3 will be the correct answer. Option C will be the correct. Okay, then moving further, next question. Okay, so for an ideal refrigerator and ideal heat pump with same temperature range, which of the following statement is true or relation is true? Okay, so already we have derived this. COP of heat pump will be equal to COP of refrigerator plus 1, right? Okay, so this is true. So these are not. So option A will be the correct answer. So this is the correct one. Then, so next, a real gas is like to resemble the ideal gas behavior at which condition, right? So when can we treat the real gases as an ideal gases, right? So this we can treat when we'll be having the temperature is more and pressure is very less. Okay, if temperature is very high and pressure is very low, in that case we can treat the real gases as an ideal gases, right? So let us check other options. Low temperature, no. Low temperature, no. High temperature and high pressure, again no. High temperature and low pressure. So option D will be the correct answer. Okay, next, so density of, okay, so let us try to understand it very properly, right? So density of a sample water is supplied, right? The density of a sample water is supplied is found to be greater than the density of saturated water at the same temperature. Okay, density of sample water is supplied is found to be greater than the density of saturated water at the same temperature. Then the thermodynamic state of the sample is what? Okay, so let's try to draw the property diagram, okay, in between your temperature and specific volume, right? So we are drawing the property diagram in between temperature and specific volume, right? We'll be getting some curve like this. Okay, so if we are talking about any process which is a constant temperature, right? So we are talking about a constant temperature, right, with same temperature, right, the same temperature. So we'll be getting a line somewhat like this, right? Okay, so at this particular line we can see this is corresponding to our saturated condition, isn't it? So this is corresponding to saturated. Okay, and it is saying that the density of sample water is greater than the saturated water. So density is greater, so this is plotted between temperature and specific volume, right? Okay, so if I am saying density of your sample water is greater than density of saturated water, then in that case I can write density is what? Mass divided by volume, right? So mass divided by volume. Okay, so if we'll be writing in terms of volume per mass, then I can say that specific volume of saturated, so this is what? Sample water, right? SW stands for sample water. This will be less as compared to specific volume of saturated water. right? So if the density of sample water is greater than the density of saturated water, then the specific volume of sample water will be less than the specific volume of the saturated water. Okay, that means our thermodynamic state point will be somewhat here. Okay, so here we are having with the saturated water, and here we are having with the sample water, and the specific volume is less as compared to this one. Okay, so what is the condition of this particular water? So is it saturated liquid? Obviously not. It is saturated liquid plus vapor mixture? No. So vapor mixture will be in this region, right? Okay, so our sample water actually it is in this region, so this is also wrong. Then compressed liquid, right? So this is compressed one, this will be correct, right? So this is compressed, that means if we'll be considering the temperature or the pressure curve, so pressure curve will be moving somewhat like this, right? And here if we'll be drawing the constant what pressure curve, then it will be somewhat like this. So here pressure is more as compared to this one, right? So pressure here is more, then that is known as your compressed liquid, right? So is it superheated? No, superheated will be lying in this region, right? Okay, so hope it is understandable. So here answer will be your this one, this is compressed liquid. Option number C will be the correct answer. Okay, okay, moving further. So swept volume of engine may be written as what? So what is swept volume? So if I am talking saying that this is our so this is any cylinder, and this is TDC, and this is BDC. So swept volume is what? The displacement or the volume which is moved by the piston, right? So piston, whatever amount of volume which is moved by the piston, that is the swept volume. That means this is the region where movement of the piston is occurring, right? Okay, so how can we calculate this one? Total volume from here to here. So this is the what? Volume of BDC minus, if we'll be deducting this one, right? So volume of this one, so that is volume of TDC, right? So this will be equal to V swept, right? So swept volume equal to volume of BDC minus TDC. So option A will be the correct answer. Moving further. Okay, now here a problem, simple problem obviously. So here a Carnot refrigerator works between the temperatures this one and this one. So this is the lowest temperature and this is the highest temperature. That means we can call this is as the TH and this is as the TL. Sorry, this is as the TL and this is as the TH, right? So if the refrigerator receives this much amount of heat, right? So if it is requiring this amount of heat, or this is receiving this amount of heat, then how much work to be supplied? So this is the question. Okay, so we know there will be a reservoir which is maintained at TH, okay, and this is another the device which is doing, okay, and this is the TL. We are extracting some amount of heat, that is QL, and to do that we are providing W amount of work, so that we are rejecting this QH, right? So we are asked to find out the value of W, right? And we are given with the value of QL, right? So 1 kilowatt we are rejecting, right? And we are given with this temperature, this is 300 Kelvin and this is 200 Kelvin. Okay, so if you know the COP, so what is COP? So COP will be equal to what? Refrigeration effect, that is QL divided by W. Okay, so this one is given and this one we want to find out. So by any means, if you can calculate the value of COP, then we can find out the value of work interaction, right? Okay, so COP can be found out for Carnot cycle, right? So basically Carnot refrigerator we are talking about, which is on a reversible cycle, right? For reversible cycle we can write the COP as what? TL divided by TH minus TL. So TL it is given to us as 200 and TH minus TL, which is 300 minus 200, that is equal to 100. So if we will be doing this, then COP we can found as 2, right? And that means I can write QL by W, that will be equal to 2. Okay, so W will be equal to QL by 2. So QL is given to us as 1 kilowatt by 2. So W can be found out as 0.5 kilowatt. Done. So here option A will be the correct one. Okay. Now next question. The net change in internal energy in a steam power plant is what? Okay, so what is the net change in internal energy in a steam power plant, right? So steam power plant, it is a cyclic device, we know, right? So steam power plant, it is a cyclic device. Okay, and for a cycle, what is the change in internal energy? Okay, so internal energy, it is a property of the system, and this is what? A state point function, that is point function. So if this is a point function, and if you are calculating the change in internal energy for a cycle, then that should be equal to 0. Okay, so change of any point function for a cycle, that will be always equal to 0. So option number C will be the correct answer for this particular question. Moving further. Okay, so this is the direct formula which is asked over here. The heat pump operating between the high temperature T1 and the lower temperature T2, what will be the COP, right? So let this is maintained at T1, and this is the heat pump which is rejecting from T2 heat, right? So this is let Q2, and this is Q1, and we are providing W, right? So what is the COP for this one? Again, so for this particular COP, we can write COP equal to heating effect. So heating effect, that will be equal to Q1 divided by the work input. So work input, I can write this is Q1 minus Q2 again. So if we'll be talking about the reversible cycle, then I can write this is T1 divided by T1 minus T2. Right? So T1 divided by T1 minus T2. So option A will be the correct answer. Then the refrigeration system works on. The refrigeration system works on zeroth law, no. First law, no. Second law, right? So refrigeration system works on the second law of thermodynamics, right? So refrigeration system, we are getting idea about the refrigeration system in the Clausius statement of second law of thermodynamics, right? So here second law of thermodynamics will be the correct answer. Okay, now so this is the direct statement question. The heat required to melt 1 ton of ice in 24 hours will be equivalent to what? So this is the definition of 1 ton, right? So ton of refrigeration, what? The amount of heat required to melt 1 ton of ice in 24 hours. Okay, of course at 0 degree centigrade, right? So option A will be the correct answer for this particular question. Done. Okay, now question number this one. So here, okay, so here which of these is an output of the furnace? So what we are getting from the furnace? Okay, so furnace basically we are using in case of a power plant, right? So there is a furnace and boiler. So heat is supplied from the furnace to boiler, obviously. So inside the boiler there may be furnace, right? So furnace, we are doing the combustion process, right? So combustion of the boils, we are burning the coals, right? And after that combustion, what will be going out of the furnace? This is the question. So fuel gas, right? So that is fuel gas, right? Actually we are not using any fuel, liquid fuel. So if this is not liquid fuel, then I cannot write that fuel gas, right? And air also not going out. Flue gases, right? The burn flue gases, whatever, suppose this is the combustible combustion chamber, and there will be some coals which are burning, and after this burning the flue gases will be going out of this particular chamber, right? That is furnace. So okay, so from the furnace our flue gases will be going out. Option number C will be the correct answer. Okay, now so I think this is the question which is repeated, and a reversible refrigerator works between temperature range same, and the refrigerator receives this amount of heat, receives this amount of heat, that means it is taking this amount of heat. Okay, and what is the work requirement? Again this will be the correct answer, 0.5 kilowatt, right? Okay, so this is a repeated question. Now, what kind of a process, okay, what kind of a process does a steam power plant undergoes? So already I have discussed about this in this particular question, right? Okay, so let us do it. Okay, so a steam power plant, already I have told you that this is a cyclic device, right? So there are a number of process occurring during a cycle, right? So from that we can say that the steam power plant undergoes a cyclic process, right? So option number B will be the correct answer for this particular question. Then, so last question, I think this is, so it is saying that heat pump is used to what? So why we are using the heat pump? Definitely in case of a heat pump, we want to heat any our ambient, right? We want to heat ambient or the refrigerator space or our area of interaction, right? Area of interest, right? So heat pump, it is not used to produce work. Basically it is not doing work, although we are supplying some amount of work. Okay, to transfer heat from the high temperature reservoir to no, right? So this is the function of your basically okay, in case of your engine, right? We are extracting heat from the higher temperature reservoir, right? But in case of your heat pump, we are taking heat from the lower temperature reservoir, right? Okay, to transfer heat from the lower temperature reservoir to the higher temperature reservoir. So option C or third option will be the correct answer for this question, right? So heat pump is used to transfer heat from the lower temperature reservoir to higher temperature reservoir. Okay, so hope you could understand all these questions, how to solve, how to approach. And during the discussion already I told you some of the concepts. Okay, so kind of it was revision of your first and second module. Hope it was interesting. Okay, so try to study as much as you can. If you will be facing some doubt, you can ask at any time, right? Okay, so thank you all, keep studying, keep preparing for your exam. Thank you.